Hello everyone, I'm Wen. Today I will present the work from our group for the file systems through two-dimensional input space exploration. So let's first talk about what is file systems and how users use it. So normally, we usually store the data on a disk image, and then we need to first mount it through the operating systems where the file system module is installed. And then the image is mounted to a specific folder, and then users or applications or operating systems can access it by invoking some system calls. So here, file systems expose two attack surfaces, which is the mounting operation, where the disk image is accepted, and also the operations. In real world, we see a lot of attacks against file systems. So first, by giving some malicious disk image through malicious USB drives or untrusted installation packages, the bugs inside the file system can be exploited through mounting or even auto-mounting supported by the operating systems. And we can see a lot of real cases such as some air-gapped APT attacks or some evil-made attacks. And also attackers can invoke some syscall payload on a mounted disk image to trigger some bugs inside file systems. We can see a lot of root exploits. However, it is very hard to eliminate bugs in file systems. This is because file systems is quite complex, and also it is still under active development. That's why we choose fuzzing, because fuzzing is efficient and it doesn't require much background knowledge about target, and it's also proven to be practical. However, is it easy to fuzz file system by directly applying existing fuzzing techniques? The answer is no. So first, we can fuzz images to be mounted. And there are already a lot of fuzzers like AFL or libfuzzer, which can fuzz binary blob efficiently. And also, for file operations, in fact, there are a list of system calls. So we can fuzz them by using Syscaller or Trinity. But directly applying these fuzzers to fuzz file systems is not so effective. I will explain the reason. So first, different from some other simple binary blob, file systems images are quite large as a blob. You can see that I listed the minimum size of some valid file system image here, and they are much larger than the suggested file size by AFL, which is 1 megabyte. And also, file system images are quite structured. Besides plain user data, there are also a lot of metadata which is used for managing this user data by the file systems. And these are the things we want to fuzz. And finally, many file systems introduce checksums for integrity checks. So if we just naively mutate these bytes on the image, we will violate the checksum checks. So if we directly apply AFL to fuzz file system images, we will suffer from huge I/O cost because of the large size. And also, we will rarely touch the metadata, but keep mutating this plain user data, which is not what we want. And also, all the checksums may be corrupted after any mutation. So that's why we propose our approach, which is metadata-only image fuzzing. So simply, we locate and extract all the metadata from a seed image, and during the mutation, we only mutate them. So by doing this, we will suffer from very much less I/O costs because metadata really occupies a little portion of a disk image. And also, only metadata is mutated. And because we accurately locate all the metadata on a CD image, we can easily fix the checksums after each round mutation. So next, we'll talk about fuzzing file operations. So in fact, file operations are a list of system calls to be invoked on some file objects in the image. So there are some interdependence between these two sides. File operation decides how to operate these file objects, and the file objects also decide what file operations can operate. So let's see some existing file system fuzzers, such as Syscaller. They simply run based on some static rules, which defines the definition of the system calls. So based on the system call definition, they generate some arguments which has a valid type and just run them. But in the context of file system fuzzing, it's not so effective. For example, they may generate such system calls like they create a directory, but they try to open it with read and write. Or maybe a file has already been renamed in the early stage of the system call list, but then they still try to open it and try to read it. So these operations afterwards are all meaningless. And the reason is because they only care about generating some syntactically correct file operations to operate some file objects. But in fact, file objects are also changed dynamically during the fuzzing, but they ignore this interdependence. So that's why we propose our approach, which is a context-aware syscall generation. So besides generating system calls, we also maintain the assumed status of the file system image during fuzzing at runtime. So we speculate the status of every file objects after each generated system call executed at runtime. So you can see, given a CD image, we have the first file status, and then we use this status to generate the first system call, and then the first system call may change some files, we assume, at runtime, so we will have an updated status of the file system image. And by doing this in a zigzag way, we can generate context-aware system calls to achieve higher coverage and find more bugs. And the third challenges of file system fuzzing or OS fuzzing is that existing system call OS fuzzers all fuzz the target OS in a virtual machine normally. And then they never reboot because rebooting or reverting a snapshot takes a lot of time. However, this brings a very serious side effect is they keep using aging kernel unless the kernel crashes. And then it will lead to unstable kernel execution. And also the bugs are a result of hundreds of thousands of system calls invoked in the past, which makes the bugs all very hard to reproduce. So to avoid this, our approach is to use library OS instead of running a real OS instance in a virtual machine. So normally, so here, we are not fuzzing a VM. In fact, we are fuzzing a user application. So everything becomes much simpler. We can easily monitor the coverage, easily share the test case. And also, every time when we finish testing a test case, we can easily restart the application, which has little cost. And the last challenge of doing file system fuzzing is that, in fact, no existing tools can fuzz both binary blob and operations at the same time simultaneously, which in fact are the two-dimensional input for file systems. So we propose Genus, which achieved this. So Genus found, we run Genus for 4 months against 8 file systems, and we totally found 19 unique bugs in these file systems, and which we get 32 CVEs. And during this period, we checked the Syscaller, and it found and fixed only 8 bugs, and only 1 of them is missed by Genus. So here's the list of the bugs we found in mainstream file systems on Linux. Yeah. And also, some of the bugs only need to mount a malicious image to trigger without invoking any file operations. So here I'll talk about more detail about our further Janus. So Janus accepts seed images and seed programs, and its fuzzing engine consists of the image mutator and the syscall fuzzer. And then by generating new mutated image and new syscall sequences, we use a library OS-based executor to mount the mutated image and execute the generated syscall. And if there's new coverage, we save both the image and syscall. If there's a crash, then we record also. So here, let's first take a look at the image mutator. So we always, given a seed image, we extract the metadata. And during each round, we always only mutate the metadata. And if the image helps to find some new code coverage, we also only save the mutated metadata blocks. And every time after mutation, we recombine the mutated metadata with the immutable user data, which we are not interested, to release a full-size image and mount it. And here's the details of our syscall fuzzer. So for our syscall fuzzer, this shows the composition of one test case. Not only including the program, we also save the open file descriptor and the stale file objects, and also the concrete information of all the live file objects after executing the program at runtime, we assume, including their paths, types, and extended attributes. So we always generate the system call based on the context by mutating an existing syscall in the program or appending a new one. And then after generating new system call, we should update the context, which is also included in the test case. So for example, if we want a syscall want a path, then we can check directory path or file path, or even sometimes when we open or make a new directory, we can give a new path. And then after generating the system call, we need to reflect the change to this context. So if it is open a new path, then we have a new file. And then we will also have a new file descriptor. And also, Janus successfully cooperates these two fuzzers. So we always first invoke image mutator. This is because the disk image, in fact, it represents the initial status of a file system. So after the time flies, more and more file operations are invoked, its impact become less and less. So we always mutate image first and do not mutate program. So if there's no progress, then we try to generate a new program by appending new syscalls or mutating existing system calls. So here's the implementation of Janus. So Janus is implemented based upon AFL. So we reuse the AFL's binary blob mutation algorithm, which also fit for mutating the metadata blocks. But we need to implement our own syscall fuzzer. And also, we select LKL, the Linux kernel library, as our library OS solution, which contains the syscall executor. And also, we introduce the kernel address sanitizer support into it, which is very popular for finding bugs. And also, we instrument for coverage. So our fuzzer support 8 mainstream file systems on Linux and support 34 system calls, which is related to operating files. And here's the evaluation. So first, we want to see if using a library OS is really better than fuzzing a VM. And by running for 12 hours on these 4 file systems, you can see Janus can reproduce most of the bugs after fuzzing. But Syscala fails to reproduce any of its found crash. And also, we want to see if Janus image mutator performs better. So in this experiment, we fixed the payload to operate on mounted file systems, but we only we only make JNS and Cscaler mutate the image to be mounted. And you can see JNS performs better, 1.5 times better than Cscaler on ext4 and much, much better on XFS. It's because it has checksums. And Cscaler just mutates this data on the image. So it cannot fix the checksums after mutation. So its coverage is quite low. And also, JNS fuzz the syscall better. In this experiment, we only fuzz syscalls without mutating image. So every time on the same image, and you can see also JNS performance 1.2 times to 1.5 times better on these popular file systems. And this is the overall evaluation. So in this experiment, we make JNS fuzz both input and also Cscaler fuzz both input. And here, first thing is when JNS mutate both input, it achieves higher privilege than mutated only image or only syscall. And also it performs 4.2 times better than Cscaler on following the BOTFS, which is considered one of the most complicated file systems widely used. And here we use a large seed, 128 megabytes, to further show that JNS performs better than Cscaler regarding file system quality. We believe JNS is a practical one-stop solution for all kinds of file system testing. So developers or researchers can use JNS to testing other types of file system or other operating system easily by porting our file system fuzzing core engine. And also, this work only focuses on finding memory corruption bugs, but it can be easily ported to find some other file system bugs which developers really care, like correct consistency or semantic correctness. And also, we use libraries, which also we believe is also a very good inspiration for other operating systems fuzzing research. So further work is supported by Google Faculty Research Award, and we will open source our fuzzer soon. Yeah, thanks. So any questions?
Please step to the microphone.
I have a question. You seem to take away part of the kernel so that you can do the fuzzing in userland. There are a lot of bugs especially in file system that are caused by race conditions, as we have seen from another paper. How do you deal with that?
So in fact, the Linux kernel library doesn't support SMP. We cannot launch more than one thread in this library OS. So we didn't find any race bugs, and yeah, it's just not supported. Yeah.
Any more questions? I have one question. You said that you mostly focused on metadata mutation to sort of be more efficient. Have you sort of looked at the structure of that metadata, in some sense similar to what we heard in earlier talks on sort of, changing metadata that's more likely to increase code coverage or create crashes?
Yeah, we only focus on mutating metadata because we think mutating user data seems to be meaningless to say.
I mean, is there any steering on particular types of metadata to change them?
Oh, no. We mutate all the metadata. So we parse, we make parser for each file system, and we fully parse an image and get all its metadata.
Okay, thank you.
Yeah, we don't differentiate among metadata.
All right, let's thank the speaker.